I'm setting up recording. Okay, great. So as usual, we will have our Canvas attendance quiz passcode in the bottom right-hand corner. Well, that's probably not a great color to choose. Okay, here's black of every slide. And I will start the Zoom feedback for this week based on how well you guys feel like you understood this week's lecture, so I can try to adjust speed. It looks like, okay, we're getting up to normal numbers of people. Yeah, as usual, the attendance quiz passcode is on the bottom corner of every slide and also here. And this week we're asking you on a scale of 1 to 5, how much you agree or disagree with the following statement. I am glad we took the time to learn the math concepts inherent to quantum computing. And possibly there's a second question, if you like math or not. And if you guys want to just like post in the chat whether or not you like math, I'd be interested to hear. But yeah, I think math's great. I think math is the best thing that you can have. Everything else confuses me, but math doesn't lie. It's great. I'm getting yeses all around. Thank you, Ramya and Nardas and Athena and Padraig and Diana and Ilan and Dhruv and Jade and Fashim and Mahesh and Yaritza and Mason, Calvert, Ariel. Oh, and Anantha Krishnan is in a superposition, which I appreciate. Tomas, Clark says it's okay. You know, some people don't love it, but I still like hearing. I'm getting a lot of math is sometimes good or pretty good, but not too committed, which is fair. I don't know. I feel like whenever I'm confused in something and I'm like, oh, like, is this way or is this way? If I can rederive it and just like demonstrate it mathematically, it makes a lot more sense. But yeah, okay. So I'm getting mostly 4s, it looks like, for this week's material. So that's like kind of optimal, I guess. So you guys mostly understood it, but you hadn't really heard it before, which makes sense because it is quantum mechanics and not typically taught in high school. So I will end that poll, and yeah, let's get started. So the most common question we had last week is if we tried to measure the spin along the z direction and the x direction at the same time. I realize I should try to draw this, but it's not going to go well. Like if we say that this is the, why did I draw it like that? I don't know why I drew it like that. Well, I've committed now. How am I going to make this 3D? Is this what I want? I don't know. Okay. My art skills notwithstanding, that's kind of a thing. Nice. I'm pretty pleased with that as much as I can be. You know, when I started undergrad, they actually made me, they made everyone take this like 3D like interpretation exam. Like it was graded, but it wasn't like, it wasn't like a course. It wasn't like you got a grade and like that was on your transcript. It was like if you couldn't visualize in 3D well enough by their standards, you need to take like a remediary like 3D visualization course where they just told you how to like imagine a 3D hexagon for like an entire semester. I didn't know anyone had to take it, but it just sounded really weird. Okay, so let's say that's our z direction, and then I will put like another box attempt. I'm gonna put it like here. That way you can kind of see it. This is really, really ugly, but, and then like there's another one like behind here that you can't really see. And it like goes behind here. So we have like our Z is this way and our X is this way. And I guess you can't totally tell, but the resulting field, when you add up like these two directions, if we put them like orthogonal to each other, so it's more obvious, and say this is Z, this is X, we're going to actually have a resultant field that is at X plus Z. And you can like normalize it if you want. But I guess you don't, like, if it's just like the same strength, then just say it's X plus Z. And when you try to measure a spin along this, I guess, not one of the bases we normally use, you will just end up with results oriented along the basis. So if you had a Z, I'm in eraser mode. If you had a qubit state or like a spin state that's like pointing in Z, then you'd end up with the spin state's projection along both of these like directions. These will be like your two options. So I guess it's like a little bit more oriented along X plus Z. So if you try to do like a decomposition of it, and this is like fake math, not real math, let's assume like it's like, we'll take our Z direction to be equal to, or I guess I could do real math, couldn't I? Yeah, it's definitely, I definitely could. Okay, let's just do real math. Yeah, this will be like 1/2 X plus Z minus X plus Z. So you can just like take or minus X minus Z. And this resultant field will give you like some probability, like half probability of measuring the X plus Z state and half probability of measuring the minus X minus Z state. So that's how you can do this decomposition. And that's a pretty general statement. Like it doesn't, we had a discussion about it in our TA meeting actually. We're like, is this actually general? But as far as we know, like, there's no way to perfectly simultaneously measure two different, like the state in like two different eigenbases. Like if it's just like a basis like this where it's a vector, like you can simultaneously measure it, but you're really not measuring it in either basis. Like you're measuring it in the combination of those two bases. Like it's a different basis entirely. Meanwhile, if you're trying to measure like two conjugate variables, like momentum and position, as far as no one has succeeded at least in measuring them perfectly simultaneously. And I think you might be able to prove that you can't measure them perfectly simultaneously, but I'm not sure if that's been proven or not. But experimentally, it's not feasible. So any questions on that? Sorry for my ugly drawings. You guys have, I can also like take questions as we go. So if you guys think of something on this, like don't just not ask the question since I've moved on. Like I can go back through the chat and answer questions later on. But yeah, there aren't any immediate questions. I'm going to go through what our learning objectives are for this week. So we're going to do a lot of analogies to like strings and instruments. And so you can see how this can kind of be scaled up and thought about in a classical macroscopic setting. And we're going to kind of, I guess all of this actually is like playing an instrument. And then we're going to go into the postulates of quantum mechanics, which are just like the 6 kind of assumptions that we're working under when we're dealing with quantum mechanics and all the math associated with it. And then at the end, we're going to give a quantum mechanical example on a guitar string rather than like a more like experimental quantum mechanical example on a guitar string, rather than just kind of the analogy of an instrument to like a mode and how that relates to our qubits. So with that, we have our motivation. Again, just because in case you guys are occasionally concerned as to why you're here. Why are we learning quantum mechanics? Like quantum is in the name for quantum computing, but like, do you really need to understand it to understand how a qubit works? And that's a bit of a mixed question. Like, to understand how a qubit actually works, you definitely need to understand it. But even to do quantum algorithms, like, you need to understand how superposition and entanglement work. So the basic quantum mechanics that we're covering in this course, you definitely need to know for quantum computing. But qubits are made of different objects that show wave and particle like behavior, just like an electron. They could be a single electron, but common types of qubits are superconducting circuits, defect centers in diamond, quantum dots, and this is often called like an NV, and I guess trapped ions are also common. So these are all like very different platforms. These are like literally like atoms that you like ionized atoms that you trap in like high fields and control them that way. Quantum dots are often in silicon. These defect centers are are all commonly referred to as artificial atoms, and all these are like all of them except for the actual atoms are commonly referred to as artificial atoms. These defect centers, at least for NVs, they are spin 1 like defects because they have multiple electrons. Like the levels are like defined by multiple electron states. Like they have more than one electron and more than one electron spin that you're dealing with. I guess it's a 2 electron. And then superconducting circuits are just kind of entire, like they're the most artificial and the most commonly used. But this is, I've gone in too deep with this discussion already, but I know you guys ask about it a lot on Piazza, and so I always like to like kind of ground it, because I feel like when I first was learning about quantum information, I originally came from a condensed matter physics background, and so I worked on topological insulators, which are considered very useful for topological quantum computing. However, topological quantum computing is entirely theoretical thus far. They haven't realized a physical version of it. And so when I was like, okay, if I want to actually work on a quantum computer that you can build today, what are my options? And it had like, I think information has gotten better as the field's gotten larger, but even like having a background in science, I was very confused trying to learn about these different options. But yeah, all these qubits roughly behave in the same way. And I think you've probably covered it, and well, we've covered it quite a bit, but you may have covered it explicitly in lecture. They are 2-level systems. Or that's normally what we like try to concatenate our, the right word, try to like reduce our space of possible options, just 2 levels, our 0 state and our 1 state. And so, but all these states do behave along with quantum mechanics, and all of the unique properties for quantum computing are due to the unique mathematics of quantum mechanics. So now I have another question for everyone. So first I'll ask you if you like math, and especially if you don't like math, do you like music? Do you play a musical instrument? We have many examples. I don't actually know what all of the instruments are on this. There's like some kind of orchestra, guitars, and a I don't remember what this thing is called. I don't remember what like most instruments are called, but do you play one? Do you know what kind of wind instrument the man in the middle is playing? I think this is a sitar down here, not 100%. But wow, you guys play a lot of things. I'm seeing violin, guitar, piano, kazoo. Kazoos are pretty fun. a small violin, a viola, a baritone, a harmonium, ooh, a triangle, nice, a euphonium. Wow, there's a lot of a quarter, yeah, no, like so this hopefully this will actually be very helpful knowing how an instrument works. Even if you don't play an instrument, all of our analogies are going to be kind of relating to sound and relating to like harmonic sound. So even if you haven't played an instrument, maybe you've heard a duet or a I don't know, like what's it called when there's three people? One of those things. Like you've heard like multiple people singing at once. The sound that you hear is different than if just one of them is singing, even if they're singing like, or because they're normally singing like different notes and they're off by like, I don't know, a step or like 3 steps or something. And you can hear that and it sounds quite different and it sounds a lot more nuanced, I guess. And so we're going to see how that kind of directly relates to quantum mechanics. So if you do play a musical instrument, you are in good company with, here is Einstein playing violin. He has a quote about how he would, like if he was not a physicist, he would be a musician. I feel like I hear this a lot from people that like, or I feel like there's a strong like association with physicists or like kind of scientists in general and like being very good at a musical instrument. I am terrible at music. Like they were like, oh, TAs, like you should give an example. I do have a violin. I don't want to subject you guys to it, so I will not be playing any. But I learned it in college, so it's not like, oh, I'm so bad. Like I like did not learn how to play it until like 3 years ago, and it's not in tune. So it's, if you don't play an instrument, don't feel too bad, because I played piano, I guess, when I was a kid, but I barely play any of the fancy instruments like violin. So with that analogy, I'm going to give you guys exactly how this relates to what we've been talking about. So we're going to start with just a string where we have 2 fixed points at the end. And this is the same thing as if you are playing a guitar or a violin or whatever. You'll have oscillations along these strings, and the thickness of the string impacts like what this ends up sounding like. And I guess like the tuning affects like how, like as well, like how it sounds, like how taut it is pulled, how much it is able to oscillate back and forth. So even in like a guitar, a lot of this description is going to apply very directly. So when we have a string like this where it's tied on both ends, you can have the string takes different shapes that correspond to what we call like modes on the string. So this is like we often call this like a first harmonic, second harmonic. Actually, I might be off by 1. If I'm off by 1, then I'm sorry. And a third harmonic. The whole idea is you just have more oscillations along the string between these 2 tied down points, and you couldn't have an oscillation that didn't quite make it. So like you can see this goes, the overall shape of this, oh, that's really ugly. Let me make that less ugly. I started out really well, and then it all went downhill. You couldn't have a mode that I guess went like that, like that wouldn't, that's not like even, it's not consistent. Like if you had a string that was not the same thickness everywhere, like maybe you could end up with this, but you're never going to end up with something that's offset like that. So you are restricted in what you can produce with these harmonics, or these modes that you can end up with. So a big thing that I may say unintentionally is, because it's not like it's not a phrase that we're learning, is like the idea of a second harmonic, where it's just like twice the oscillation frequency as the first harmonic. And it's a very common thing to end up with second harmonics in anything that you're doing. You create a resonator and you can end up with you can end up with like higher order modes. If you create like a resonator that operates at like 6 gigahertz, you'll also end up with a resonance at 12 gigahertz. So there's, for all these things, it can always host all these modes. And what we care about and what we'll see is that sometimes you want to reduce the modes that can be hosted. You don't want to have infinitely many modes. You only want to have one mode or 2 modes. So here is again the same kind of example with the guitar string. Apparently, this is an actual photo where you can take a picture of this with like a really fast camera, and you can see that the guitar strings do actually oscillate with these same kind of modes. So that's pretty cool. But we have a question: why do we only get these modes? Well, these modes are, rather than having any kind of intermediate frequency, these modes are a result of confinement. So because we have these like stop points on either end, these fixed locations, we are stuck with only certain modes. And these modes are actually eigenfunctions of this system. You could mathematically describe this and back out these specific frequencies as being eigenfunctions of our system. And so when we are going to no longer this quite classical analogy with like a guitar or a string, and we are talking about electrons or atoms, you can keep the same like modal analysis, same like harmonic description, because all of these particles do also behave as waves. And they are, when they are confined, like they're in one particular place, or if they have, I guess, typically when there's nothing like nearby to your particle, then you will get the same kind of quantization. If they're not confined, then you can get, or I guess, like their spatial wave function is very distributed. I'm not gonna describe this because I've confused myself just now trying to describe it. But if you guys ask later, I will give a better description. But the whole idea is just that we have qubit states that correspond to these modes. And these modes are the frequency that your qubit is operating at. So what we actually are addressing, I think I'm gonna have it drawn soonish. Oh, maybe later. Okay, I'm going to draw a little version. You could say this is your 1 state, and this is your 0 state, and then maybe you want to address actually between these 2 states. You have like a delta frequency between these, and this is at like frequency. Yes. Well, there's like 2 different ways you can describe this. But yeah, I'm gonna describe it like this. And then that's like the relevant frequency. That's where we can also just call it the frequency between these 2 states. And this frequency is equal to energy over h bar. So if you're wondering where our energies of these states come in, because everything is an energy. So to give a little bit more, I did have the 1s and 0s. That's what I thought. I had the 1s and 0s here. I forgot that I was on a slide. So I've drawn something that I already had written down. But yeah, you can, when we're dealing with a qubit, we specifically only deal with these 0 and 1 modes, and we ignore this guy because we don't like him. And what we are actually doing is specifically for I'll say for the most common type of superconducting qubit, which is called a transmon, your 2 state, which would be this guy, this omega 1, 2 is less than omega 0, 1. So if you put in a frequency that's like resonant with these modes, then we actually end up with like addressing only this state and not addressing this state. So it's just kind of like invisible to what we're measuring, even though it does still exist. So the whole way that you get rid of these higher states is you move them in energy somehow. And there's different ways that you can do that, and we may cover it later on in the course. But that is the whole thing: is we have to get rid of those modes because you will always have these evenly spaced higher order modes. And that is an important caveat to anything we're doing. Okay, so we now have our quantized systems, which I mentioned these guys earlier. Our trapped ions, our diamond and V centers, and we want to create systems that we can use for this two-level system, so we can use it as a qubit. But we have a lot of challenges, like keeping the state clean. So you want to have only like the exact state you want. You don't want to have this impact from the higher modes. You have to get rid of any noise from the environment. And you need to have a reliable way of addressing between these modes, so you can like excite, like if you give more energy to the system, you'll go to a higher energy mode. So here's some pretty pictures of what these can look like. These different levels. It is very similar to how the electrons in an atom work, and people do trap like neutral atoms and use them as qubits as well. But they're not individually controllable, so there are limitations to them. So are there any questions with this kind of overview? Oh, thank you, Kazi, for your question. What does noise refer to? Noise is absolutely anything and everything that interacts with your system. So kind of classical qubits stem from a field. I happened to be talking about this earlier today, so I'm blatantly plagiarizing one of my lab mates, but it stems from cavity QED, which is, this is quantum electrodynamics. And what people found out is if you put a two-level system in a resonator, then you can control very well your noise, because you're only getting noise at the resonance frequency of the resonator. You're not getting a bunch of noise from other sources. So I guess I don't know a great way to describe it. I guess I'll try to put it like this. I don't know if this is a super accurate way of showing it, but let's say we have like this in level and this in, let's say this in 1 and 2. If you're in a resonator, like this is kind of like the box around your two-level system. You can only get things that are resonant with your resonator, and so you can kind of isolate your two-level system from a lot of things. Yeah, this is very similar, as Joshua said, like camera noise. Yeah, when you see like, I guess I'm trying to think exactly what's happening in a camera when you see noise. Like if you're not getting enough light, like if you're taking a picture and you see it's kind of like blurry and like pixelated, that's because the sensor in your camera actually isn't getting enough light. And so you can, like if you've ever done some photography, you know, you can adjust the shutter speed, which affects how long you hold the camera is collecting light. So if you're in a low light setting, you want to collect light for a long time so that it has enough information to reconstruct the image. And so if you're in a low light setting, I guess, I don't know if it's the noise on the detector itself. That is a thing with cameras, is they actually, like there's very high tech cameras that you use for different types of imaging, like for physics applications, where you want very little noise in your camera, and you actually cryogenically cool your camera so that there's very little like phonon, like heat causing noise. You don't want to have a bunch of electrons like jumping around causing noise, because normally these, like at least like really high tech cameras are like they're called like CCDs, or charge coupled devices, where they convert your light into electrons, and then they multiply the number of electrons that they have, and that's how they get the signal. So you want to have as little effect on these electrons as possible, for the sake of having a very clean measurement. So this is even like a macroscopic thing. Like, well, I guess it is like on the individual electron level, and that's kind of the thing, is these CCDs, like normally you're trying to measure not single photons, but like very few numbers of photons. But yeah, I've gotten some other good comments. Michael has some like good thoughts. If you perform operations on a larger number of particles in unison and measure that system as one qubit, could you not have a few subsystems decohere and still have a proper measurement? It depends what type of measurement you're trying to do. So again, like we've established that you will have your state, like if you have any type of strong measurement, you'll have your state collapse. But you can do a type of a weak measurement where you only vary, like you couple to your qubit very, very little, and that will not cause your qubit state to collapse. But that is still that the channel, or the interaction of your qubit with like your readout device, which is normally some kind of resonator, which also has these resonant modes, that will also cause noise. Like it is coupled to the environment. So I guess I don't know if I answered that question at all, your actual question at all. But if you're trying to measure your entire, like all these examples we've given for qubits are actually mini particle systems. They're not quantum systems in of themselves. Like I guess there are like single electrons involved in like these defect centers, like there's like 1 or 2 electrons involved. Similarly with the trapped ions, there's like generally like 1 electron on like the outer shell, or like you have two energy states depending on whether you have an electron there or not. So they are like single electron, like the state that you're reading out is the single electron state, but the actual thing you're addressing or like interacting with is like a whole chunk of diamond. So you're shining light at a diamond, and you are reading, in many cases, many electrons. Like you'll have many of these defect sectors that you're reading out. And you can still measure that, but you don't have a, like depending on what you're doing, it's no longer a coherent measurement, because you're measuring too many and you don't know the relative phase of each of them. So that's a big thing in like diamond quantum information, is you're trying to have like single defect centers so you can just address one. That's kind of the thing with, I guess, qubits in general, is you generally want like one quantum state that you're measuring. You can have many particles involved in making that state. So like in a superconducting qubit, you have a whole circuit that's like a big amount of aluminum in some shape, but the actual state you're measuring is one singular quantum state. So that's a different, I guess, like it's a nuance, I guess, to think about. But yeah, thank you all for your wonderful questions. I will move on to the postulates of quantum mechanics, but we can go back to this because I think this kind of physical realization is a really important point for how these systems are actually implemented in the the reasons why we care about some of this stuff is not obvious unless you know what the physical system is like. But yeah, so the postulates of quantum mechanics, which you guys covered in a lecture this week, are that our quantum state is represented by a wave function, normally represented by a psi, and that's our wave function postulate. Our classical observables are operators in quantum mechanics. So for example, energy goes to your Hamiltonian, which is an operator. We don't normally hat it just because like we assume it's an operator. And if you see like this hat, that means it's an operator. And the meaning of that, I guess, is it's quite nuanced. I guess I don't actually know a general way of describing what an operator is, but I think it was covered in lecture. The only possible results of measuring an observable are the eigenvalues of the operator that you are using to measure. So if you, like that's like the whole thing for measuring on the z-axis with our Stern-Gerlach experiment, we can only measure our z-basis eigenvalues. And that is another postulate. And these are all just like assumptions that we are working with. We've never found anything that is in opposition to these postulates. There are a couple that are a little bit more not controversial, but I guess controversial, honestly. Like they've sparked a lot of debate as to what they actually mean. We'll get to that in just a second. The probability, these four are not those. I'll point out the ones that are a little bit more controversial, I guess. So the probability of observing an eigenvalue is equal to this equation, like that's not what I wanted. I don't know why we wrote this out rather than this. And that's our probability postulate. So that's often called the Born rule also. And again, these are things that we've just found to be true. Why are they true? Why is the speed of light 3 times 10 to the 8 meters per second? I don't know, but it just is. Like you can derive exactly how you get to that number, but that it all involves measuring something at some point. So that's kind of these postulates are, as we've observed them to be true. Next, and this is kind of the more spicy take, I guess, is that after measurement, our quantum state is equal to the eigenvector corresponding to our observed eigenvalue. That's our collapse postulate. The meaning of this has been argued a lot. Like there's like a many worlds interpretation. There's the Copenhagen interpretation. There's a lot of different ways that people have interpreted this. I don't find it that upsetting as a concept, I guess. And there are people also, like with regard to kind of like this noise thing we're talking about. There are people that don't really believe that it truly collapses, but that it just actually gets washed out because of like it loses coherence for that state, but your like measurement apparatus has like functionally gotten a version of that state and then added a bunch of noise to that state system, and like that's somehow that's actually what you're measuring. But that's not a widely believed view, but there are people, like there are theorists who believe that. So that's kind of argued over. And then our final postulate is for the time evolution, one of these eigenstates. So these eigenstates can be like, there's also like different ways of describing them, but a common way is to describe them as being stationary in time, and then you can evolve it in time by applying an operator to it. So you do that with, I guess, like you can do it like this, or you can say that your state at time t is equal to your state at time 0 times e to the I h bar t, and that's like our unitary evolution. So it depends on how you'd like to write it, but these are pretty much saying the same thing. Yeah, so now to kind of try to tie this in a little bit to the Stern-Gerlach experiment. So this is the same slide from last week, if you remember it. And this is the same idea that when you measure it, the spin always has a direction along the direction of the magnetic field or the one opposite to it. So you have, I guess, changed the quantum state to whatever direction it should be. And that's kind of the same idea as like collapsing your wave function. I guess the non-obvious results is like if you say, okay, my quantum state, like I can see like my position has changed. My observable in the case of the Stern-Gerlach experiment is my position. It can be up here or it could be down here. Just because you measured the eigenvalue, like it does, I guess it's obvious mathematically that it works out that you should get your eigenvector, but physically it's a bit weird. Like, why do you end up with the eigenvector that corresponds to that pure like up state or that pure down state rather than your wave function remaining the same? And I think in a large part, all of this is, I think it makes sense overall mathematically. Sorry, I dropped my pen. It makes sense mathematically, but the physical interpretation is really what's controversial. Everyone kind of likes how it works mathematically, and it makes very good sense mathematically if you have a good understanding of how the mathematics works. But all of these, this whole experiment, you could kind of reframe in terms of the postulates. For example, like our position like corresponds to an operator. Now we're, and I guess that operator, well, I guess we'd probably want to, I don't know, it's a bit hard trying to give a direct analogy, but we could say like our spin state and our magnetic field are operators. Like our magnetic field operator acts on our spin state, and then the observable that we're actually measuring, which is our position, is affected by like the trajectory of our spin state being affected by the magnet, which is an operator, and then you can perform a measurement on the system to get out your resulting position based on all of these factors. So when we actually want to do this measurement, how will we do this? Well, if we know that our observables are operators. So I guess we're claiming like the phrasing in this that the observable is spin, which I guess is also fair. Like I guess what we are measuring is spin, but what we're detecting is position, and our position is dependent on our spin. It all depends how you'd like to phrase it. But when we want to describe these in terms of operators, we can say our spin along our z-axis is our z operator, our Pauli z operator. This, what is this letter? This letter. And that corresponds to our Z matrix, which is this 1, 0. Thank you, sigma. Thank you, Anantha Krishnan. I am having a struggle of a night, apparently. Our spin along our x-axis is similarly our sigma x, or our x operator. And our spin along our y-axis is our y, or sigma y operator. And these have the same matrices that we've seen many, many times before. And so when we actually want to measure these spins, we can use our observation postulate, which tells us that the only possible results of a measurement are the eigenvalues of the operator that we're using. So if we are measuring in our z basis, we can only get 0, like the 1 state or -1 state, or you can also call this spin up or spin down. Or we can also put this in, oh, sorry, these are our eigenvalues and eigenvectors in blue. It's color coded, but I'm so used to just doing things as zeros and ones that I'm very thrown by it being off by 1. Similarly, these are our plus and minus states. Let's say this is our plus state, or our 1 state, and this is our down state or 0 state. And then we have our y operator, which it's just the x operator with a phase on it, but we don't normally assign like a fun name to it, but that is also an option if you wanted to measure in y. But you can kind of get all the information you want with our z and our x states, because one is, I guess, measuring an arc energy basis if you're in like a qubit, and one is measuring the phase if you're thinking about it on a block sphere. I don't know why I decided to do it with a pen rather than, it's like this is our energy, and these are our phase. This is our 0 state, this is our 1 state. Yeah. What a beautiful drawing I just made. Yeah, so that's how this measurement will go mathematically. And we can check this, actually, I should have drawn my block sphere a little bit farther up. We can check this with applying a z-gate on our 0 state. So the result of this would be doing 1, 0, 0, minus 1 times 0, 1. And you can run this mathematics through. I'll give you guys a second to do it in the chat. You can see the results, I guess, already on the slide, but it's good to do it by hand, and I'll work through it as well. But what you want to do is multiply this 0 by this 1. That gives you 0 plus 1 times 0 gives you 0. And then that's our top state, I guess. Times 0 gives you 0 plus 1 times -1 gives you -1. And that's equal to 0, -1, which you can also decompose into our beginning state. So if we want to make it an eigen state or eigenvector, then we need to put it back in terms of our 1 state, or sorry, our 0 state. Our 0 state is equal to 0, 1. Therefore, our resulting, I guess, z0 is equal to -1, 0. Sorry for this being so cramped. That's our result. And that's how we get to this. It's the exact same thing. But yeah. So now, if we want to think about what our options are, and we've kind of we've given the answer mathematically, but I guess trying to think through it more like as an interpretation or like in words. If we are measuring with a spin along the z-axis, what are our possible outcomes? And we've given you the operator matrix and the eigenvalues and eigenvectors. So let's say like we're trying to measure our, I guess we can just call it the eigenvalues. I'm not going to be bothered if you treat them as just like the state as well. But what are the possible outcomes if we're measuring along the z-axis? And the observation postulate is important for this. Not getting any answers. Maybe I didn't phrase it super well, but I'll try to give an overview. Oh, I think I actually gotten from Tomas. Yes, saying 1 and -1. Yep, these are our possible eigenvalues. These are what we can measure. So our observation postulate is that the results of our measurement are always eigenvalues of our measurement operator, or like our observable measurement operator. So our only possible options are 1 and -1. These correspond to our 0 state and our 1 state, but we can also so I guess like our 0 state and our 1 state are the eigenvectors, and these eigenvalues of 1 and -1, like obviously it doesn't correspond to a negative energy. It just corresponds to like 2 different energy values. So this will always be true, even if you're not in the z basis, you can be in the x basis, and the same thing will be true. So now we have our kind of secondary problem, which once we've measured along the z base in the z basis, and we've gotten a spin of -1, which like corresponds to our 0 state, what will be the wave function immediately after the measurement? Will it still be whatever it was beforehand? Like it could have been anything that we were measuring. We just happened to measure once that it was in the 0 state. So what will our wave function be after measuring? I'm getting some good answers. Thank you, Eric and Athena, Mason and Robert. I think you guys are all right on track. So again, this is our 0 state. This is our 1 state for the sake of consistency. And you can also refer to them as their eigenvalues. So if we know we've measured the -1 eigenvalue, we know that we're in the 0 state. And because of our collapse postulate, which says that whenever you perform like a measurement on a state, and I will specify for like nuance's sake that it needs to be a strong measurement, you will always collapse to the state that you measured. So you're functionally projecting your quantum state onto the axis of like your measurement operator. And so we know that if we measured -1, we are going to be in the 0 state, and it's not going to go back to being in whatever state we started with. We're going to be in the 0 state from this point on. So now with that, we're going to go back to the Stern-Gerlach experiment, where we're going to have our superposition state of this like half 0 state, half 1 state. So it's this is the same thing as a plus state, and this is just an equal superposition of being up or down along the z-axis. And we remember from last week, hopefully, where this electron should go based on this. Does anyone remember or just know, like looking at this, where our electron will end up out of these 5 numbers? Getting some answers. Thank you, Kazi and Angel. Mason. I'll give you guys another second to think about it. I know I'm not going to get through all the optional content it looks like today, but I can stay a little late to go through it. Ooh, thank you, Xavier and Christian and Fahim and Carmen and Snehil and Joshua. Yeah, so what's going to happen is if our electron, which is in a superposition of the upstate and the downstate, goes through, well, the downstate is going to go down to 3, the upstate is going to go down to, or is going to go up to 1. And these are both going to happen with a 50% chance. And you can honestly think about it as being these 2 discrete states going in, like in over here, like maybe it's in like some question mark spin, like who knows where it is, like it's all over the place. But as soon as it enters the magnet, it's going to align to the magnetic axis and it's going to be in one of these two states. So that's the best way to think about it, I think. I hope I'm not belaboring the point too much, but it is, I think, quite a confusing idea. So now, if you want to convert this back to our kind of mathematical representation, we have the same state represented as this psi. We have our operator matrix, which is Z, so we're doing a Z basis measurement. And then we have our eigenvalues and eigenvectors listed. And what is the probability of measuring the electron that's in state psi being +1, and what is the probability of -1? If you are unsure of how to calculate this, you can, I guess, take your psi like this. That's your probability. And so when you're actually performing the measurement, you're going to be, like for the +1 state, you're going to be taking, let's note this is 1 and this is 0. For the +1 state, you're going to be taking the probability is equal to the absolute value of your 1 state with your 1 state squared. Or I guess like, well, we also need to include our normalization. Let me, I'll say this is times 0.71 squared as well. And our -1 is the probability. I'll write this one better than the last one, I guess, is equal to 0.71 times your 0 state and your 0 state squared. So you can do this math. It's pretty straightforward because these inner products will be 1 because they are in the same direction. Remember, everything is normalized, so both of these are 1. So the only thing you need to do is take the square of this 0.71. So if one of you guys would like to do that, you can tell the answer. And you're going to get a little bit of a rounding error. So thank you, Tomas and Joe. Yeah, this 0.71, there's more numbers after that, is about 0.5. This is an approximation. You could also take this as 1 over the square root of 2 is like the accurate descriptor. So you will have 0.5, 0.5. So this is a 50% chance of being in either of these states. And so we can mathematically perform this this spin state measurement, I guess. And I guess I kind of didn't do like the important bit almost, where you actually do want to apply your Z gate to your psi state, so that you will, like, to do it like properly, like rigorously, you should multiply your psi by your Z gate, and you'll get the same result. So you could, I guess, do like 1, 0, 0, -1 times. I guess I'm just gonna do a big bracket and do 0.71, 0, 1 plus 0.71, 1, 0. And then you can like perform that operation and do all of that. And you want to keep like these two components separate because they are different states. They don't just like kind of blob together. Yeah, this, like, you can do a more rigorous way of doing it than how I showed it. Yeah. Oh, and I've written over words as usual. It's fine. I know where the words are, but I always think I avoid them, and I never do. The key takeaways, though, for this this lab is that when a system shows wave-like behavior, and the wave-like behavior is confined, the wave modes get quantized, and so you only have discrete values that they can take. At the scale of electrons and atoms, everything shows wave-like behavior, and so everything shows quantization when confined. And these postulates of quantum mechanics we've gone through are rules that we have found all these quantum systems follow, and you can just take them as kind of a given. So We have some further reading, and I'll send out these slides later tonight. And the lab will be posted on YouTube, and I think they're going to send out the link. Are there any questions on this content? And I will do the post-lab Zoom feedback. And then for anyone who wants to stay, just because we're doing a recorded section, I'm going to go through the optional content, which is just a little bit more kind of guitar analogy. It'll probably take like 10 minutes maybe. Oh, cool. I've launched the poll. Yeah, because we're slightly over time already. So this is the end of the regular lab content. If you want to watch the optional content, there will be 2 versions of this lab uploaded to YouTube, so you can watch either. And but I'm still going to go through them today. Yeah, thank you for all your feedback. Things. It looks like I'm seeing far fewer 3s, so I guess I did a decent job today. I'm never sure if I'm just rambling, but I hope that everything is useful to you guys. And thank you so much for attending. If you're leaving now, I'm going to just keep going through the optional content for the sake of our recording. Yeah, so to go back to where we were, we have our wave function postulate, where a quantum state is represented by its wave function psi. And we can kind of go back to this analogy with a guitar string, where we want to pluck a string. Nut and bridge are just 2 stationary points, and you're going to create a ripple on it. And so you can take this ripple to be a wave function of the guitar. And so in this case, we've taken it to be this this like kind of Gaussian, like peak. Gaussian is just a certain shape of a peak. If you haven't taken probability, you probably haven't run into it, but a bell curve is a Gaussian. The whole idea of a Gaussian is just kind of goes to 0. It's not like a standing sinusoid. So when we want to describe this ripple with the eigenfunctions of the guitar, so we can say this is our actual shape that we have. We have our 2 fixed points, and we have just this ripple that is at just one particular location. But that's not an eigenmode of the system. That's not like, if we want to think of the system as oscillating, we know that the string is oscillating. Obviously, this isn't the real shape, because this isn't a function that is suited to our system. Like, we know that any of our, if it's an eigenmode, it needs to be like this, or like this, or one of the other options. And so I'm going to, what I just drew, I'm going to have come up on screen again, where we have this ripple is equal to some combination of all of the eigenmodes of the system. So this resulting shape is actually many, many different eigenmodes. And if you are familiar with it, if maybe you've covered a little bit more advanced like signal analysis somehow, or some more advanced mathematics, this we often refer to as taking the Fourier transform of the shape we get, and we can decompose it into these resonant frequencies. We can decompose what frequencies we're actually seeing, rather than just this arbitrary shape that we've directly measured. So we can start out with just like our first order mode, and then we can add our second order mode, and we'll get this shape where we now have this kind of like offset lump. That's obviously not like an eigenmode of the system by itself. The eigenmodes are all shown, I guess, over here. And this is like measured. And then we can add our third mode. See, it's getting kind of closer to what we're measuring. We had our like 4th and 5th mode. And now we've added up to mode 8. And you can see it's really converging towards this shape that we measured originally. And if we go up to 10, it gets even closer. And so you can see if we increase the number of modes, the match improves and improves. So maybe we want to have all of these modes combine to actually describe our system, or maybe we want to throw out some of these modes for I guess computation purpose. So all these modes, regardless, are in a superposition of, or this I guess this ripple is in a superposition of all these modes. You can describe this exactly in the same way as we describe a superposition with a qubit. So if we had an equal superposition of our 0 and 1 mode, so we say this is our 0 state, this is our 1 state, this is exactly what the mode would look like. So that's pretty cool. We can, and this is of course for our guitar 2-level system, or a resonator 2-level system, but it would look exactly like this if we used a guitar as for that purpose. So we can now go back to a qubit a little more explicitly and say that we have our equal superposition of these two states. I'm just knowing this is Fourier analysis. So this, again, would be our 0 state, and this would be our 1 state. And so when we are measuring a qubit, though, we know the only possible measurement results are the eigenvalues of its operator. So we would never, we'd never be able to measure this like Gaussian shape in a qubit. But on the guitar, we actually will see, I guess, the opposite. We're only going to see, or I guess, yeah, I guess it's actually true. Like on the guitar as well, we're not going to see the resulting ripple. We're going to see a certain mode of the system. Like when we see this oscillation, like we're never seeing the total mode that is all these, or the total ripple that is all these modes combined. So similarly, when we think about probability, the probability of observing a certain eigenvalue, you can mathematically describe like we always do. And for a guitar, the probability of seeing a certain mode depends on its contribution to the ripple that you saw. So maybe the ripple is like a slightly different shape, and this one has like 0.7 of your 0 state plus 0.2 of your 1 state plus 0.1 of your 2 state. So the amount, the probability that you measure any of these 3 states, you're obviously not quantum, even though I put them in Broadcat notation, is proportional to the amplitude. So these are amplitudes. And I guess the big difference between a guitar and a qubit, I guess, like is the amplitude, like you don't have to square the amplitude when you're, the reason that you have to square it, or like part of the reason you have to square it for a qubit is that well, it's not part, well, okay, I guess it's not necessarily the reason you have to square it, but if you were trying to measure the energy of your different modes on your guitar, you would also square this amplitude, because energy is the amplitude squared. I don't think it's necessary to be squared, or it is necessary to be squared for a quantum state, but I don't know if it has to do with it being the energy. That is something I will read up on and confirm or deny next week. But yeah, this does kind of carry over almost exactly to a guitar. Similarly, if you are measuring a quantum state equal to the eigenvector corresponding to the observed eigenvalue, you can also look at the guitar string, and like even though the total modes of the guitar string you're looking at may have a certain ripple, it does still have all these modes that you might be observing. So it is similar, although not quite the same as a quantum state collapse. Like you do still have all of these observed options, I guess. So with that, that is all of our optional content. I can take like one question if you guys have anything pressing. Otherwise, I hope you have a wonderful week. Yeah, I think this last slide it's a bit sketchy the way it's phrased, I guess. But it is like overall a good analogy, I think. If there aren't any questions, I hope you all have a good week. I'm going to stop my screen sharing.